This will be a co-presentation by Luca and I. So this is some of the work we did together when I was at CISA, and also that we continued afterward, and that led to the creation of Step 7. So Step 7E is about, so hopefully my mouse will keep on working. Okay, so Step 7E is about how we can handle non-matching methods between independent, fully distributed grids. So it's a highlight of what we can achieve with this type of approach. So I guess maybe first we'll give some context, and actually we'll kind of be able to figure out that everything ends up reducing to point evaluation, and we'll see what type of process we use to manage that. Then we'll go more into the fluid structure interaction problem and how what we did could be extended to much larger problems and much more complex physics. And we'll quickly discuss the results for Step 7E and just show what it is we achieved. So first, I guess some context and some motivation. So I am a chemical engineer by profession. So when we talk about multidisciplinary research, I think deal.II is a great example of that. And one of the applications we work a lot with is what we call mixing. So from the pharmaceutical to the cosmetics to the chemical industry, we have mixing applications. So you mix a fluid and you hope that all the different components you have will be blended together. And it turns out, I think I can repeat the animation. Just give me 2 seconds. So I don't know if Luca is clicking at the same time as I am, which makes things even more confusing. So I think, okay. So what we see here is a color rtree experiment. So you inject a dye, in this case, it's a purple dye. And what we will do is you will insert an acid component that will neutralize this indicator, and you will see how much time it takes for the mixing to actually occur. And what we generally teach to chemical engineers is that, well, mixing is instantaneous and you don't need to worry about it. But actually, for the majority of industrial application, it's a pretty clear bottleneck, and it can lead to severe waste. I think for the North American industry, the money lost alone due to poor mixing is estimated to be in the order of $2 to $3 billion annually. So it's often a severe bottleneck. It's difficult to investigate experimentally because you need these clear tanks, which are very difficult to set up, and it's not so trivial to simulate. So the reason why, so there is a slight delay in the slide switching. So the reason why it is so difficult to simulate is that the rotation of the geometry prevents the use of arbitrary Lagrangian Eulerian techniques. So you need to have specific techniques to take into account the rotating impeller. So some of these are a change of reference frame. So this means that you're simulating in a Lagrangian rotating frame instead of in the laboratory frame, but this imposes severe limitations on the geometry. Other approaches which are generally used in Fluence or OpenFOAM would be to use a sliding mesh, in which what occurs is you have two non-overlapping grids and you couple these grids at the interface. So what we decided to go with this step is to look into non-matching methods. So Luca and I have a long history on working on immersed boundaries or fictitious domains approach, and this is a very good opportunity to leverage that. But non-matching methods, they are also a lot more powerful, and they can be used for a much broader range of applications. So they're very strong for fluid structure interaction, also let's say flows in blood vessels, or very complex fluid structure interaction where the deformation of the solid body can be nonlinear, let's say hyperelasticity or etc. But they can also be used to simulate overlapping geometries. And in our group, we have a lot of projects with dough mixer manufacturers, so people that create mixers that are used to blend bread dough or cookie dough. And these are very complex geometries in which the swept volume of the two, let's say, impellers, they are intertwined. So what is the basic principle behind immersed boundaries? So a quick graphical summary of that. So the problem we wish to solve is we have different properties on different domains. So we have a fluid domain, in this case it's going to be the green domain, and we are going to have a solid domain, which is going to be the orange domain in the illustration above. But even though here we explain it in the context of a fluid problem, it can be actually any type of problem. It's just that we have different properties or different physics on two different domains. So for instance, the green domain could be a fluid and the orange domain would be a solid, whether it is a deformable or a non-deformable solid. And the problem can itself be intrinsically multi-scale. So what we need is we need a numerically efficient way to transfer information between the domains without necessitating a matching grid between the domains. So we wish to embed the orange grid within the green grid or the blue grid without having any matching between the two. This allows us to lift any type of restriction on what type of problem we will be able to solve or what type of deformation we will be able to simulate. So how do we proceed? We're first going to need a way to track points. So in the end, all of this is going to reduce to a tracking point problem. That is, we're going to have to track information on the solid domain, for instance, that is going to lie on the fluid domain. So the idea Luca and I took was to use particles for this. So particles, they're an ideal tool to keep track of the motion of our embedded domain, because they can readily move from one processor to another using MPI sum-to-sum communication. They already contain inherent efficient mechanisms to detect in which shell they lie and then deduce their reference location. And we can attach an arbitrary amount of properties to them. So for instance, velocity, or actually, as we will see, we will be attaching information to the particle that will allow us to bring their information back to distributed MPI vectors. So we start with our basic background grid. So in our case, this will be the grid which we will use to solve the fluid problem. So this is our background domain, which we will name omega. On top of this domain, what we do is we add an additional domain that we generate also using the grid generator, to generate from name and argument grid generator. So what you see here is exactly the problem we will be wanting to solve. So we will have a background fluid domain omega, and on top of this fluid domain, we have an additional non-matching domain, which will be in our case, our rigid impeller, but could be any type of could be representing any type of other physics. This domain, on this embedded domain, on the solid domain, we calculate the position of the quadrature points, and using this, we generate a list of the quadrature points that lie within the embedded domain. And these quadrature points are the ones that are converted to particles. And as you will see as we go on further, we only need to attach a very limited amount of information to these particles. So now we took an embedded grid and we transformed it to a series of particles, and now we will have the mechanism to, as these particles move or are advected or displaced or deformed, we will have a mechanism to locate where they are located and to interpolate the information of the background grid at their location. So the first problem that we face is that we will need to insert those particles. So we wish to do these simulations in a fully distributed environment. So one of the challenges that we face is that not only is the background grid distributed, so it's a parallel distributed triangulation, but also the grid that we are using as the embedded domain is also distributed. It's also a parallel distributed triangulation. If we wish to do a full fluid structure interaction problem, this is necessary. Otherwise, we would need all of the subdomains of the parallel triangulation for the fluid domain to own the entirety of the solid grid. So, and this would eventually not scale very well. Imagine if you had 100 core or 1,000 core, and each of these core had to carry on the full solid triangulation. This would never scale to large problems. So the issue we have is we have two domains that do not, seems like, so we have two domains that do not match. And not only that, but the points of the embedded domain, they can lie in a cell which belongs to another processor. So what we need is we need a global insertion mechanism that can create particle from a vector of point where each processor owns a vector of points. So we start from each processor owning a vector of points, and we figure out in which location, on which processor these points lie, and in which cell they belong. So This is one of the major additions that Luca and I wrote that appeared through step 70, is the insert global particle function within the particle editor. So the insert global particles is a very simple function that starts with 3 arguments. So we need a vector that contains the location of the particles that this processor, the processors want to create. But we do not impose any restrictions on these points. They can lie in an arbitrary cell, or they can lie in an arbitrary processor. We just need these points. We need a n processor size vector containing a vector of bounding boxes, and these will be used to accelerate the location of the particles. And finally, we have a vector of particle properties. And using these 3 simple ingredients, we're able to fully generate the particles without any previous knowledge about on which processor they will be lying. So I guess, Luca, maybe you can take it from there.
Yes, so can you all hear me, I think? Hopefully, yes. Okay, so the way that we proceed in this thing, so this is particularly concentrated on the second argument that you see in the previous slide. So the second argument is the global fluid bounding boxes. So the idea is that if you have a coarse grid and you want to figure out where a point lies on the grid, one way you could use to achieve this is to use an rtree of bounding boxes, and Boost offers such a construction. And trees basically are data structures that allow you to identify in which box a particular geometrical entity satisfies a certain property, like, for example, it belongs to the box is one of the properties you can ask, or it intersects the box if you ask for another bounding box. And it does so using a logarithm of the number of boxes times. So you could in principle use this for, to identify on a serial process what are the number of particles, what are the cells that actually contain a given particle with a very good accuracy by just constructing, as you see here on the right, a full representation using bounding boxes of your triangulation. Or you could use this as a very coarse representation, like what you see here on the left, that you can then share with all participating processors to actually compute some, to have some rough idea of where I should send particles, and not to send, to avoid at all costs all-to-all communications. This is exactly the second argument that is passed to that function. So the second argument that is passed to that function uses basically that represents a very rough representation of your geometrical domain in terms of global bounding boxes that are the smallest number of boxes that can show how your MPI processes own your area of the domain. And as you see, some of these boxes are overlapping. So if you have a point that happens to fall in one of these 3, here you would have 3 bounding boxes that correspond to the 3 processors. So the algorithm will say, okay, the point may be owned by one of those 3 processors. So this is a very difficult case, and it's the case of the guys that happen to be here, up here. This is a, obviously very bad if you use a very small number of boxes. As you increase the number of describing bounding boxes for, to describe your algorithm. So for example, if you look at the center here, this very large overlapping is becoming less and less frequent. And what's going to happen most often is that you have one, for most of the particles, you know exactly who to send the particle to. And for some of the particles, you have 2 possible receivers of the particles, and for all the particles you have instead 3, and that's basically the largest number that you should get with the types of discretizations that we have with the p-forest implementations that we have in the library. This allows you to the generation of these boxes starts from creating a rtree of the boxes from the locally owned active cells, and this is exactly a snippet taken from the step 70. So what happens here, we just loop over all boxes over all locally owned active cells of our triangulation, and we store in a vector of bounding boxes all the bounding boxes associated to each cell. We construct an rtree of these boxes, and then we extract one of the first levels, which is what you see here of this rtree. This gives you a very good representation of how the bounding boxes, what are the bounding boxes that actually cover your domain. And this is used by the algorithm that distributes particles all over the places in order to avoid communications between more than 2 points. So most of the communications that happen in that case are point-to-point communication. And once you have done this type of things, the insert-global particle, it's really just a matter of gathering the number of particles to be added on each one of the processor to identify which cell and on which processor the particles are located. And this is done by a call of distributed compute point locations, which takes that argument as an input. And then gather the properties of the particles from the original owner of the point. So this, all of these things are done to the insert global particles call you've seen before. Now, once you have this, the outcome is that you have a very flexible particle insertion mechanism in which you, so this is an example that is provided also in the step 70 parameter file. So you can actually run the simulations with an impeller that is coming from an open source project for COVID-19 lung respirators, in which you could actually have this type of geometry, and you could download that for free. So we created a grid for that. And then we created a parallel distributed triangulation on the solid. And then we distributed all the particles belonging to, well, just to the boundary of the solid, not to do all the volumetric part. So as long as you have a triangulation, even if it's not matching, now you can use it to insert particles. Well, before, what you basically had to do was to guarantee that the particles were generated only locally on the fluid domain where you were wanting to have the particles at the end. So how is it going to happen that we keep track of the ownership? So the way that we do this is by leveraging linear algebra in the background, since we have very good linear algebra packages that do in a very efficient way pattern communications, and they are very good at doing this type of stuff. What we do basically is that we store in a linear algebra, in a LAC MPI vector, the particle positions. So we store the coordinates of the particles in the following way. So what we do is that for processor blue, which is the one that we have here, we store locally only the particles that are owned by processor blue. So these are the locally owned particles that you see here. And all particles that happen to fall on the same blue domain may be accessed to a ghost element. So we keep track basically two vectors, one which is a read-write vector that contains only the locally owned particles, the blue ones, which we assume to be equally distributed between the processors because you created them starting from a parallel distributed triangulation in the first place. And if you need to read information from those things, the reading information is done through storing the index set that contains the indices of the coordinates of the particles that fall within your domain inside ghost elements on the linear algebra vector. So with two index sets objects, which identify locally owned particle coordinates and locally relevant particle coordinates, which are the brown dots in this example here, we are able to keep track of the ownership of the particles. And then this is done at the initialization, so the first step. We do this either by distributing the particles according to what is the owner, the solid owner, or maybe distributing the particles at the beginning, deciding who owns the particle according to who owned the particle in the first step. So this is what we do in step 70. If you wanted to enable step 70 to actually do full structure interaction problem, then we should use the second step, which is somewhat easier because the ownership is constructed on the first time when we generate the vector of particles, and we have the index set, which is basically constructed by simply storing the starting index and finishing index of each one of the particles or of the particle coordinates in each of the processors. And once we have these things, we can initialize a parallel MPI vector with it. And this can be used to exchange information. For example, if you want to update velocities, we have created a interpolate field on particles that actually takes a DOF handler, distributed DOF handler, a particle handler, and it takes a solution that allows you to read all particles, or a solution that allows you to store, to save in the particles all the locations that are locally owned by the single domain. So if you do it this way, these tracer particle velocities can be used as you would normally do with standard LAC MPI vector, and the result is simply that the all the relevant communication happens when you construct a locally relevant version. So when you construct a ghosted vector version of the particle velocity versions that you see here. And this construction, so this copying in the Gauss vectors, so updating the Gauss values, is where all the communication happen, and it's really hidden behind the scenes. So it's very transparent to the user in a certain sense. And now from the fields to the particles, we have interpolated from the particle, and then instead from the particle to the fluid, in some sense, we can to the vector, we can do the other way around by doing set particle positions using the relevant tracker particle displacement. So it's a two-way coupling in which we can transfer information from the fluid to the particles and vice versa. So if we put it all together, we decided to make as simple as possible a step example. And basically the only three ingredients that are necessary are the ones that we already shown here. So we need to initialize particles with a given triangulation or with more than one triangulation. And this is exactly what happens in step 70. And then the type of equation that we solve in step 70 are just Stokes flow for creeping flow, in which we impose weakly with the penalization parameter that U is equal to G on gamma. Here, gamma represents an impeller, which is a mixing device, which is embedded in the domain and not necessarily coupled with the domain. So you can do these things in several different ways. So what we have done in the example is the simplest possible approximation that we could think of. And this comes basically can be derived from Nitsche approximation by taking some approximations. And what happens is that this works both in the case of codimension 0 and in the case of codimension 1. And in the example, we actually show both codimension 0 in 2D and codimension 1 in 3D. So in both cases, the formulation that results is the standard Stokes equation. So I won't spend any time in this because this is taken verbatim by any one of the Stokes problems in the library. So it's exactly the identical thing done here. And plus there's two terms, which is beta VU over gamma and beta VG over gamma, where both V and U are basis functions of the fluid domain, but you want to integrate them on the solid domain. So you need to somehow have to keep track of what are the position of the solid domains, but only of the basis functions and basis function values of the test functions on the fluid domain on the reference positions of the solid domain. So, and this is where particle handler comes in very handy. And so what we do is the following. The assembly of the Nitsche term, which is the only difficult part of the tutorial, step 70, is done by looping over all particles cell-wise. And in order to do that, we basically exploit the fact that internally the particles are stored is an unordered map of cells versus particle, and which means that you can very easily and very cheaply gather all particles that lie within the same cell. And we start with the first particle, we query what is the cell of the first particle, and then from then on, we loop over all particles that belong to the same cell, and this is a very fast loop, which is done cell-wise, only over the cells that actually own some particles. So this is what's written in step 70 and shows you how to extract information from the cell particle. And the only thing to notice here is that in order to provide the integration of these two terms that you see here on the right, the only thing that is really necessary is to store the Jacobian times W of the solid cell on the particle themselves. So if for any quadrature point of the particle, you store J times W of that particle, you can actually compute these integrals over here by simply querying what is the basis functions that actually is different from 0 on that quadrature point and just summing over all those quadrature points, which is exactly what is happening here. So we collect for every particle the point, which is the reference quadrature point, the real quadrature point, and the Jacobian times W weight, which is the thing that we actually need to do the integration. And then we perform the integration, which is best done by not even instantiating an FE values, because we can just use the finite element space directly using the shape value I at the reference point Q, which is returned by the particle itself, times J times W, which is the weights times the quadrature points. This is very similar to what you would have done if you had the FE values of the solid. But instead, we are doing this on the fluid. And the same is true for the right-hand side on the penalty parameters, on the penalty terms on the right-hand side, which is the one that actually moves the solid. So it is a fluid structure interaction problem with a sum approximations, in the sense that we're not giving feedback to the solid, and the solid is just moved with an imposition of the velocity on the outside. So the idea that we wanted to reproduce was the mixing problem in creeping flow regimes. And this is a fantastic experiment, very famous experiment that was done by Sir G.I. Taylor using colored dyes. And after that, you could see thousands and thousands of similar experiments in YouTube. And if you actually look for them, there's a lot of them which are very, very cool, and they look very, very nice. But the principle is that for Stokes flows, since they are linear flows, the dependency in time is just a parametric dependency. So if you revert the action of time, you should revert history. And so if you start with mixing in Stokes flows and you go 5 times in one direction, and then you turn the motor on the other direction, you should get back to the same position at the beginning. So this is a very cool way to verify that what we have constructed and what we have created actually works as we would expect from the physical point of view. And this is exactly what we wanted to try and test. So this was basically a check, something to check that everything was done correctly. And of course, if you look at the way this works in step 70, this is exactly what you get if you run the default parameter file for step 70. We rotate an impeller, which is made by the fluid particle that you see, the violet particles. Is that violet? Yes, maybe. Violet particles that you see here, which they represent the quadrature points of the solid particles. And after you've done this, oh, actually, this is now showing me too fast. That was background. Yes. So you see that the final position should be identical to the initial position. It's not exactly identical to the initial position. And we track 2 different particles in the solid. One are passive tracers, and we use exactly the same technique that we use for the solid tracers. And one are the solid particles, which we use which move ourselves with something which is given from the outside. And the solid is just the velocity of the fluid is just imposed using penalization parameters on the fluid. And as you see, the resulting bow, it's of course, it's only a first order scheme, so we should have higher order schemes in this case to get better conservation properties. And the number of degrees of freedom is very small, so this simulation runs in something like 2 or 3 minutes. So it's notwithstanding the fact that this is a very fast simulation, and it's a very nice property. I think it shows the power of this type of method. And this is a 3-dimensional simulation that took a little longer to run, something like between 5 and 10 minutes instead of a few minutes. And it was just a rapid test to show that we can actually do this on very complicated geometries on 3 dimensions. So I think that the take-home message of step 70 at the end is that we try to basically demonstrate a large variety of concepts without really trying to concentrate on the best fluid structure interaction problem approximation. However, if you want to do fully massively parallel distributed fluid structure interaction problem with no matching methods, you will have to pass through exactly the same steps that we have shown here, plus the addition of the solution of an elasticity problem on the solid and the coupling between the two, which, however, can be done in a way which is very similar to all the other steps, as long as you have a way to couple the 2 problems efficiently. And what we are showing here is that one way which is very efficient is to let the linear algebra classes do the coupling and the message passing on the background for you. And this will be true. And it's true also for the matrices, whenever you have the matrices to couple between the 2 things, as long as you can provide an initial global insertion of particles where you initially assign ownership of every one of the particles. And now we didn't show it here, and maybe we should have, but if you look at the time spent by this program in performing the various integration steps in 3 dimensions, you will see that the actual time spent on moving particles around is basically negligible with respect to the rest of the simulation time, which is the solution time. And I think this is well, it shows two things. One is that we're not good at writing preconditioners for these massively large problems, which means we should probably concentrate a little more on getting less than 1,000 iterations in order to solve the problem. But this is a difficult problem because of the presentization that we have there. And second is that this can actually be used competitively if you have massively parallel inverse boundary methods. So I think this is all that we wanted to say. I don't know whether Bruno has something else to add. Let me say that this is something that it was extremely fun to work with, and I really appreciate the opportunity that we had in the last hackathon, in the last deal.II workshop that was happening in Colorado. We met with Bruno, and this is exactly the outcome of that collaboration that started on the last deal.II hackathon. So this is also a good example of what you can do with people that you meet at this type of things. It's going to be difficult today for this online meeting and online workshop, but keep in mind that these are exactly the type of things that happen and that are very, very good. You know, it's a very good experience, in my opinion.
Thank you very much to the two of you. This too is cool, and I think there's two takeaway messages for me. One is that if you provide infrastructure like particles, people are going to use it for things that nobody anticipated, and that just open new doors to very cool applications. And the other part is I appreciate that you point out the fun collaborative work, because that's really what I have always found over the last 20 years, that it is fun to work with other people. And I hope that if deal.II enables this, that's fantastic. So we have time for questions, both for this particular talk and for anything you ever wanted to ask about deal.II. I think I at least plan to be here until the end of the hour, and so I'll probably do many others. So if you have questions, type it in the chat box or just ask.
And maybe we should start with questions for Luca and Bruno.
Yes. "52 people online, and not one has a question. That can't be right."
We are all stunned by the really cool animations, I guess.
I think so. I think we have to, I want to carefully read that example step now.
Same, yeah.
So there is one question. There is one question. So how efficient the method gets around itself is. So it depends. We have several methods of that type. So the gets around in cell, actually it's called find active cell around point, to be precise. And the find active cell around point has internally a lot of tricks that have been very generously contributed by René, and that actually accelerate its speed a lot. So I think it's pretty efficient. It only fails to guess the correct cell for which to compute the expensive parts very rarely. And I would say for a very large computation in which you have particles, that you have many particles move around, the computation of the inversion of the cells, which is what is used in gets around or find active cell around point, is covers about 30% of the total computational cost if you have millions of particles. But maybe René has a better answer for that. He's the one that contributed in this algorithm in the state that it is currently. Actually, in another deal.II hackathon, the one previous, the last.
Yeah, that's right. So it depends very much on which application you are thinking about and what's the situation when you want to know the surrounding cell. So the call to the function getSurroundingCell is actually extremely cheap because each particle already knows the cell in which it is in. So that's why Luca said the real question is how expensive is it to find this association in the first place? And this can be done very cheaply if you know an old cell of the particle. So if the particle has only moved a bit, then you can look for cells surrounding the old cells, which is much cheaper than looking in all of the cells in the local domain. As Luca mentioned, if that fails, then you have to go to more expensive algorithms. And one way is, for example, to look for the closest vertex of the whole local triangulation and look for that. A different approach would be, so in the worst case, in distributed triangulation, it might not even be in the local triangulation. It might be on a different processor. And that was what Luca was referring to when he talked about the rtrees and the trying to first find the processor on which this particle is on and then find the cell on that processor. So it depends very much on the application and the situation.
It's an excellent question because you cannot imagine how much time Renee actually spent on implementing this. It is one of those things that end up being a page in a publication, but actually, I don't know, a month of work behind that. There's a question by Ignacio Thomas, whether this could be used to implement particle in cell methods, for example, electrically charged particles coupled to Maxwell. Luca, do you want to answer this, or should I?
I mean, you're the one who created the last examples with the particle in cell method that actually does something very similar, right?
Okay, so I will answer it. I should start by giving Renee even more credit than he just deserved for the find active cell around particle, or whatever the name of that function is. Renee implemented particles originally for a code called Aspect that solves convection problems in the Earth's interior. And only later were these particles, was this particle functionality moved into deal.II. So this is his child, really, and he should get the credit for it. The origin is exactly what you suggest, Ignacio, that it is particle in cell methods, where these particles track properties. So we were interested in solving problems where you want to track the chemical composition of a piece of material that is moving along, for example. And so the chemical composition would be something that you attach to a particle and then you move the particle along. So the origin of all of this implementation is in exactly these sort of methods. And there is a tutorial program that we started last Thursday on the first day of the hackathon. That's going to be step 19 that shows a very simplified version of this, where I'm just tracking electrons in an electric field. So that would be what you would call passive particles. Namely, they just move along with the field and you make them active if the particles also interact with the field itself. So if there's the feedback from particles into the field, which in this case, because particles are electrically charged, of course, they have an effect on the electric field. And I added that yesterday and it added, I don't know, 12 lines of code or so. So yes, what you suggest is possible and is going to be finished, I don't know. It always takes longer than we think to finish a tutorial program. Let's say 2 weeks, maybe 4 weeks. And then it's going to become step 19.
Okay, great. Thank you very much for the answer.
Right, Ignacio, if you want, I can also add something else. So if you take a look at the step 70 parts, which are relevant for tracking particles and maybe putting some feedback in the equations, the other side of the thing that Wolfgang was saying is exactly what we do in step 70, where particles actually have an effect on the equations by basically adding a penalization term on the fluid equations. Is like adding a velocity force on the fluid equation. So it's exactly the same type of things, and it's exactly the same type of, you would implement it exactly in the same way. So typically you would have a Dirac delta source at one point, which is centered on the location of the particle, and that Dirac force you will compute as X action on the test function, which is V computed at the particle, which is exactly what I showed in the slide in step 17.
Okay, great. It's good to know that that capability is there. I might come with questions in the future. It looks like a very interesting capability, and of course it looks very non-trivial. How to have a list of who is owned and where is it owned doesn't look like something you can code on the weekend. You need a little bit more time than a weekend.
Absolutely
No.
not. I think Rene probably spent a good year of his life on that.
Yes.
And he's too young, but if he was a little bit my age, then he would have gray hair from it for sure.